Yeah, let's get started then. So yeah, this is a picture of one of the 7 concourses at the Hartsfield-Jackson Atlanta International Airport. Now, Atlanta International Airport is the busiest airport by passenger count in the United States, in fact, in the world. And it's held this position for 24 out of the past 25 years. It sees more passengers in a single day than most commercial airports see in an entire year. On an average day, ATL lands and departs more than 250,000 passengers. It fuels 1,700 flights each day, which is a takeoff or a landing every 60 seconds. Now, these stats are already incredible, but Atlanta International Airport was in the news last year for pulling off something even historic. The nearly 50-year-old Concourse D at ATL was meant to serve smaller planes. But in Hartsfield's meteoric rise to becoming the world's busiest airport, the concourse grew increasingly cramped. This is when ATL decided to undertake a $1.3 billion expansion of Concourse D. They planned to widen the concourse from 60 feet to 99 feet and extend its overall length by 288 feet. Now, obviously, construction requirements from the airport and the airlines mandated that Concourse D remain operational with only a limited number of gates being taken out of service at any given point in time. Now, to meet these requirements, WSP, which is a consulting company, which was serving as a project manager for this project, they built the concourse modules at a remote location at the airport, while at the same time working on the needed foundation and utility relocation works at the concourse. Now, as you can see in this picture, large self-propelled modular transporters crab-walked these 700-ton modules 1 mile across active runways to within inches of the concourse. Incredible engineering, right? Well, good evening. We already did the introductions, but that's me, Jimmy Morzaria, and I'm presenting with Yuli Zhang, who's my co-worker. We've worked on online databases at Stripe for the last 4.5 years. In this talk, I want to zero in on DocDB, which is Stripe's internal database as a service platform built on top of open source MongoDB. We'll dive deep into our zero-downtime data movement platform and how that has helped scale our database infrastructure to power trillions of dollars of payments annually. This platform has been absolutely critical for us in that it has enabled a major architectural shift at Stripe. So we moved from running our MongoDB shards like a few pets that needed constant manual care to running them like a large herd that can be automated and scaled easily. Just like how the Atlanta International Airport moved those massive modules into place without missing a flight and scaled a cramped concourse to support thousands of more passengers per hour, we'll be talking about how we scaled our critical Tier 0 database infrastructure to support trillions of dollars of payments annually. And it's really humbling to share the work of so many infrastructure engineers at Stripe today. With that, let's begin with a quick introduction on what Stripe is. Stripe is a financial technology company that allows businesses around the world to accept payments online and in person. Over the years, Stripe has built a fully integrated suite of financial and payments products, such as billing and subscription management, card issuing, usage-based billing, and more. Now, you can see here some of the largest companies in the world, including Amazon, NVIDIA, OpenAI, Google, and Shopify, rely on Stripe to process payments. Our mission at Stripe is to build the infrastructure to power commerce around the world and to grow the GDP of the internet. Now, to that end, Stripe has facilitated over $1.4 trillion of payments in 2024. And as of today, Stripe is powering 1.55% of the global GDP. There was just a website refresh at Stripe today where we are actively now displaying the percentage of global GDP that's getting processed by Stripe. So really cool stat. And we strive to process the staggering volume of payments with 5.5 nines of reliability. Obviously, reliability is extremely critical when it comes to processing payments. We've seen that research shows that 40% of customers whose payment is abandoned or declined will abandon that business entirely. And the impact of unavailability goes beyond just losing money. It has the potential to have a lasting reputational impact. Now, at the heart of Stripe's 5.5 nines of reliability at $1 trillion scale is robust tier 0 infrastructure, including networking, compute, and databases. Our database infrastructure handles over 5 million database queries per second. We have petabytes of critical financial data, which is distributed across more than 2,000 database shards. So the question is, how do we go about scaling our databases to handle millions of queries per second over petabytes of critical financial data with 5.5 nines of reliability? Now, the answer to this question really lies in our journey. So let's go back in time and take a look at the history of database infrastructure at Stripe over the years. In 2011, Stripe launched with MongoDB as the online data store. This allowed us to move quickly because MongoDB offered better developer productivity and automated failover capabilities compared to standard relational databases at the time. Back then, product applications spoke directly to MongoDB shards, and we only had a handful of MongoDB shards. Fast forward to 2017, as Stripe grew, our fleet had expanded to tens of MongoDB shards. These shards were holding data for many different use cases, with some of the data still remaining unsharded, while a lot of it was getting sharded. More importantly, all of the maintenance operations in 2017, such as spinning up new database shards, replacing nodes, building indexes, so on and so forth, were still being handled by engineers with ad hoc scripts. This was obviously becoming a reliability and scalability bottleneck. This is when we built the database proxy service in front of our MongoDB shards. While the key motivation to build the database proxy service was connection pooling, the proxy layer was always meant to be more than just that. We envisioned the database proxy layer to act as a single point of interface between the product applications and the MongoDB shards, and to enforce concerns of reliability, scalability, admission control, and access control. This diagram illustrates our architecture in 2017, where you can see the database proxy servers are acting as a critical central layer between the product applications and the MongoDB shards. Moving on, the year 2020 marked a significant shift. There was an exponential growth in online commerce in 2020. This chart here is from an annual letter to our shareholders, where you can see the number of companies and businesses signing up for Stripe with .ai as their top level domain started increasing exponentially from 2019 and 2020. Now, this is just businesses with .ai as their top level domain. But we experience a similar exponential increase in businesses relying on Stripe to process payments across sectors. But what does this really mean for our database infrastructure? The result was a corresponding and steep increase in the number of queries being sent to our database shards, along with a significant increase in the overall storage footprint. Initially, we supported the increased throughput and storage by vertically scaling up our database shards, with some shards reaching tens of terabytes in size. And this strategy worked really well for a long time until we inevitably started running into the limits of vertical scaling. And it quickly became clear that adding more database shards was necessary to keep up with Stripe's exponential growth. And to tackle this challenge, we needed to invest in some key foundational building blocks. These new components included building a control plane to provision and deprovision databases and shards, create and drop indexes, and run other maintenance operations on the database fleet. It included building a routing metadata service to map database partitions to physical shards. And finally, we invested in data movement capability. Together, these components provided the foundational technology to scale our database infrastructure horizontally with the growing needs of our business. And here's what our database infrastructure looked like in 2022. Product applications still talk to their databases through the database proxy servers. However, instead of a static map from database partitions to shards, we now have a routing metadata service that the database proxy layer consults to route queries to the appropriate shards. The shards themselves are deployed as MongoDB replica sets with a primary node and several secondary nodes which are distributed across availability zones and regions. We've also shown the control plane here that's responsible for provisioning databases and shards, building and dropping indexes, and running other maintenance operations that we spoke about. And finally, we have shown the CDC systems here, which are responsible for transporting the write-ahead log, or as MongoDB refers to it as oplog, from the MongoDB shards to Kafka and eventually to S3. So data from our CDC pipeline is used to power our offline and analytical use cases. In 2023, we put this technology to test by performing online data movement at scale, proving the robustness of our system. And today, thanks to these efforts, our database infrastructure at Stripe, built on top of open source MongoDB, is highly reliable, scalable, performant, and efficient. As DocDB, which might be confusing to many because there are several products out there which are called DocDB at AWS and other companies in the industry, is essentially a composition of all of these components that we spoke about and a few others that are not shown here or illustrated here that come together and allow us to offer a database as a service to all of product engineering at Stripe. So a natural question to ask here is, why spend all of this time and effort building a database as a service in-house versus buying an off-the-shelf offering? And to be honest, at various points in Stripe's 15-year history, we've considered leveraging off-the-shelf database as a service offerings. But the reason why we've invested in building something in-house versus buying something off the shelf really came down to three different things: security, reliability and performance, and scale. So first up, let's talk about security. For a financial platform like Stripe, security isn't just a feature, it's everything. Building DocDB allowed us to bake in security right from the start, and specifically through the robust enforcement of authorization policies right at the data layer. Next was reliability and performance. MongoDB is an extremely powerful document database and has a large surface area in terms of its querying capabilities. Now, if you don't use these querying capabilities in the right way, you can have unintended reliability and performance bottlenecks. Now, the strategy that we took was to only expose a minimal battle-tested set of database functions to our engineers to prevent these unintended reliability and performance bottlenecks. This approach also allowed us to offer true multi-tenancy with enforced quotas, which means that one user's database activity cannot inadvertently impact another user's. And finally, of course, scale. DocDB was designed with a focus on seamless horizontal scalability with sharding, ensuring that the business need for growth are met without compromising reliability and performance. With that context, let's take a look at the logical constructs that a product engineer interfaces with when interacting with DocDB. There are two main logical constructs, that of a logical database and a collection. A logical database is essentially a container of related data housing one or more collections. Whenever a product engineer needs a data store for their service at Stripe, they create a logical database and a collection using an internal database management console. Now, the database management console talks to our DocDB control plane to provision the logical database, the collection, and the backing infrastructure. While creating the logical database and collection, product engineers also specify a shard key. In this example, you can see merchant, which is highlighted in purple down there. That's the shard key. So this is an example database which is named core payments, and there's a collection in it called payment intents. This is not a real collection in our database. This is just an example, but sort of serves the point here on how we think about logical databases and collections. Now, under the hood, data in a logical database and collection is sharded across several database servers. The way we do that is by dividing up the key space for a shard key into several different chunks, each of which houses a contiguous range of data. So in this case, we have sharded the logical database core payments and collection payment intents into two partitions. So documents with a shard key belonging to the key range 1 to 50 will live on shard A, and documents with a shard key belonging to the key range 50 to 100 will live on shard B. We call this table the chunk map, and each row in this table is called a chunk of data. And this chunk map is stored in the routing metadata service. Okay, so far we've looked at how Stripe scaled its database infrastructure to support more storage and throughput by first vertically scaling its databases. And we also looked at how we built some key foundational building blocks, such as a control plane, routing metadata service, to automate database provisioning and other database maintenance operations. But how do we go from here to horizontally scaling our database infrastructure? And to take a step back, what is horizontal scalability? It's essentially distributing your data across several different database servers. We saw that in our example, database, we started off with two sets of shards. Now, if we need more storage and throughput, we somehow need to divide and distribute the data on these shards across many more shards. And obviously, we need to do this in a manner that's transparent to product applications, does not result in any downtime, and does not have any performance implications on the user queries that are already being sent to the shards that we want to split. Now, to address all of these requirements, we built our zero-downtime data movement platform, and Yuli will walk us through the details of that.
Cool. Yeah, thanks, Jamie. Before we dive into the mechanisms of the zero downtime data movement, I want to call out a few design principles that really shaped our approach. First is consistency. So throughout the migration, we need to know what the data is kept complete and correct, and that it stays consistent between the source and the target shard as we move it over. And the second is availability. So millions of businesses rely on Stripe to take payments 24/7. So downtime during data movement just isn't an option. Our goal was to keep the critical phase of the migration very short. Specifically, we wanted to be shorter than a plan-based primary failover. And we wanted to fit within the retry budget of our application layer. That way, from the product's point of view, it's at most a brief blip, not an outage. So the next is performance. When we move data between shards, we need to make sure the migration doesn't slow down the shards involved. We want to preserve their throughput and latency, so product queries continue to behave normally while the migration is running in the background. And finally, granular and adaptable. At a Stripe scale, we can't design this for one migration at a time. We need something that works no matter how many moves are happening across a fleet. So we built it to support moving any number of data chunks from any number of source shards to any set of target shards. And we don't want artificial limits. So no cap on how many chunk migrations can be in flight across a fleet, and no cap on how many migrations a single shard can participate in at once. We also needed to handle real-world data sets. Some chunks are small, others are huge, and several of our shards hold terabytes of data. So the system has to move large chunks at high throughput without falling over. With those design principles in mind, we designed a blueprint, starting from first principles for moving data across MongoDB shards with zero downtime. Before we get into the details, I will quickly walk through the high-level flow. First, we register the intent to migrate a specific chunk of data in the routing metadata service. This is basically us saying this chunk is moving and establishing the source and the target. Next, we take the point-in-time snapshot of that chunk and use it to do a bulk import into the destination shard. After that, we start replicating all writes that happened after the snapshot. We keep streaming those changes to the target until it fully catches up. At that point, the source shard and target shard should be in sync, and they should contain the exact same data. So we run an exhaustive correctness check to confirm the data is complete and consistent. Once we are confident everything matches, we orchestrate a traffic switch in our database proxy from the source shard to the target shard. And finally, after the cutover is complete, we deregister the migration from the routing metadata service, so the system no longer treats it as in flight. So now let's zoom in and walk through the steps one by one. Step one is registering intent. We tell the routing metadata service exactly which data chunks we are going to move, where they are moving from, and where they are moving to. Think of this as the system's source of truth that a migration is about to happen. Once that's recorded, we prepare the destination shards. Concretely, we build the necessary indexes on the target shards for the chunks we are about to copy, so the target is ready to serve reads and writes as soon as we cut over. In this example, we are scaling out to increase throughput, so we register migrations for chunk 50 to 75 and 75 to 100, and we assign them to two brand new shards, shard C and shard D, highlighted in pink. The next step is bulk data import. We take a point-in-time snapshot of the chunks on the source shard, which is shard B in this example. And we then use that snapshot for bulk loading the data onto the target shards, shard C and shard D. This step sounds straightforward, but in practice, we run into real throughput limits on MongoDB ingest. We tried the usual fixes first, batching writes and tuning storage engine parameters to make bulk insertion faster. None of that moved the needle enough. What finally worked was changing how we route data. MongoDB storage engine lays data out using a B tree, so insertion order matters a lot. we started sorting the snapshot data by the most common index keys and then inserting in that sorted order. That made consecutive writes land much closer together on disk, which cut down on random I/O and page churn. And the result was a big jump in bulk load performance, about a 10 times improvement read throughput. Once the snapshot has been bulk imported into the target shard, we start replicating incremental writes. Concretely, we stream over every write that happened on the source starting at the snapshot timestamp and apply these changes on the target. Our async replication systems read the uplog on the source shard from the CDC system, change data capture, and issue writes to the target shards. There are two reasons why we consume uplog events from the CDC pipeline. The first is that we don't steal read throughput from the user queries on the source shard. And the second, we are not constrained by the source shard's uplog retention window. We also built a replication service to be resilient to target shard unavailability and to support starting, pausing, and resuming synchronization from a checkpoint at any point of time. And finally, the replication service exposed the functionality to fetch the replication lag, which will be useful in a later step that we will talk about in a minute. Now, any mutation on the data undergoing a migration gets replicated bidirectionally from the source shard to the target shards, and from the target shards back to the source shard. The replication service tags every write it applies on the target. That way, if those writes show up again in the change stream, we can recognize them and ignore them. And so we don't end up in a circular asynchronous replication loop. The reason why we built bidirectional replication is fast rollback. After we cut traffic over to the target shard, we still want the source shard to stay up to date. Then if we run into issues on the target, we have a fast and safe option to switch traffic back to the source without losing writes. Once replication has caught up and the source and target are in sync, we run a thorough correctness check. We do that by taking point-in-time snapshots on both sides and compare them for completeness and consistency. Using snapshots is important here because it lets us validate the data without burning read throughput on the source shard or impacting query performance. Once the validation comes out clean, the next step is the traffic switch. This is orchestrated by a coordinator. At a high level, the cutover has three things that need to happen in the right order. First, we briefly stop traffic to that chunk on the source shard. Then we update the routes in the routing metadata service to point that chunk to the target shard. And last, we have the proxy layer start sending both reads and writes to the target shard. The way we make this switch safe is with a protocol called version gating. And here's the core idea. Every request the database proxy sends to the shard includes a version number. That version number represents the routing metadata version the proxy believes is current. On the other side, each MongoDB shard also tracks the routing version it considers current. And it enforces a simple rule. It will only serve requests whose version is at least as new as the shard's version. So if a proxy is still using the stale routing config, its requests carry in an older version, and the shard will reject them. That forces the proxy to refresh its routing metadata, and it prevents traffic from accidentally going to the wrong place during the cutover. So let's walk through an example to see how this works in practice. In steady state, each database proxy layer annotates request it sends to the shards with a version number, in this case, version number 1. The database responds with the result, which is then forwarded back to the client application. Now, to update the route for a chunk of data being migrated, we use the coordinator to execute the following steps. First, the coordinator confirms with the replication service that the replication is running and healthy, that writes are actually actively flowing from the source shard to the target shard, and the target is staying up in sync. This is the replication lag functionality we mentioned earlier. Once it received a successful response from the replication service, it then proceeds to bump up the version number on the source shard. The version number is stored in a document in a special collection on the MongoDB shard. At this point, the client's query are still tagged with routing version 1, and the proxy continues sending all reads and writes to the source shard. These queries start getting rejected by the source shard because the version number 1 is stale compared to the version number 2 on the source shard. The database proxy service receives the stale version error, which is forwarded back to the client application as a retrievable error. Next, the coordinator checks with the replication service again to ensure any outstanding writes on the source shard have been successfully replicated to the target shard. Once it gets a successful response from the replication service, the coordinator updates the route for the chunk in the routing metadata service to point to the target shard. As part of that change, it also bumps the routing version from 1 to 2. After that, the database proxy server fetches the new routes for the chunk of data being migrated from the routing metadata service. Now, when the proxy gets a query for the chunk of data being migrated, it forwards it to the target database and shard with the version number 2. The target shard responds to the database proxy service with a result, which is then forwarded back to the client application. The entire flow switch protocol takes a maximum of 2 seconds to execute, and all failed reads and writes directly to the source shard succeed on the retries by the client application. There's a couple of things to note about the traffic switch process. First, we have made custom patch to our fork of MongoDB to implement version gating. Second, remember that replication is bidirectional. We're keeping the source and target shards in sync in both directions. That means rollback is symmetric. If we ever need to move traffic back to the source shard, we can run the exact same traffic switch process in reverse. Operationally, that makes rollback fast and simple. And finally, once the cutover is complete, we persist the routing state in the routing metadata service. In this example, that means updating the shard mapping so that key range 50 to 75 points to shard C, and the key range 75 to 100 points to shard D. And here is the end state. We have scaled out our fleet from 2 shards to 3 shards. Let's do a quick recap of what we've done so far. We started with data on a single shard, and we split it up and moved it onto 2 new shards. At a high level, the workflow is take a snapshot, then bulk load that snapshot onto the new shards, and then replicate every new write to the new shards until they catch up, and verify correctness, make sure we didn't drop or corrupt anything, and then switch reads and writes over to the new shards. The key takeaway is once you have this zero-downtime data movement capability, it unlocks a whole set of powerful infrastructure use cases. So far, we look at how we can use zero-downtime data movement to scale horizontally by adding shards. With this platform, we can take an existing MongoDB shard, split it into multiple new shards, then gradually move data and traffic over without taking downtime. And the nice thing is it works in the other direction too. If those shards become underutilized, we can use the same workflow to merge multiple shards back into a single shard. At Stripe, we rely on this heavily to handle our biggest traffic days, especially Black Friday and Cyber Monday. Another thing we can use with this platform for is MongoDB major version upgrades. By moving data from a shard on one version to a shard on a different version, in an ideal world, you'd just upgrade in place. And you often can. But usually, only one major version at a time. Most databases won't let you jump, let's say, from version X to version X plus 3. You have to go step by step. That's where the zero-downtime data movement platform helps a lot. Instead of doing a long sequence of in-place upgrades, we can stand up a shard on the target version, migrate the data over, and then cut the traffic over when we're ready. At Stripe, we use this approach to upgrade our entire fleet, more than 2,000 MongoDB shards. We are skipping multiple intermediate major versions. That saved us a lot of time because we could bypass versions that didn't meet our performance needs. And there's another big benefit, rollback. If we see issues on the new version, we have a straightforward and fast way to move traffic back to the original shard. And next, we also use a platform to migrate database between multi-tenant and single-tenant setups, both directions. For example, product teams often start on a shared multi-tenant database to move quickly and keep costs low. As product gain traction and its scale or isolation requirements increase, we can use the data movement platform to migrate that workload to dedicated single-tenant infrastructure with minimum disruption. And if priorities change, we can also migrate in the other direction, consolidating back to multi-tenant setup to simplify operations and improve efficiency. The same data movement platform can also support data tiering. At Stripe, we found that a meaningful portion of our data is infrequently accessed. Still, when it's needed, it has to remain available through the same query interface without requiring users to change how they query it. By moving this code data to lower cost storage, we can reduce overall fleet cost while preserving access patterns. The data movement platform lets us archive rarely accessed data transparently. So teams get the same experience at query time where they optimize storage behind the scene. And I'll hand over to Jimmy for the key takeaways.
All right, so wrapping this up, I'd like you all to go with 3 takeaways. First, reliability is non-negotiable. At Stripe, we obsess over the reliability of our APIs, and that has proven to be a key differentiator for our company. We design and build systems with reliability front and center. And in this talk, we looked at how our data movement process is designed to have zero downtime for our product applications. Second, invest in strong foundations. We saw that the ability to migrate data across database shards in a manner that is transparent to product applications and has zero downtime enabled us to not only use it as a tool for achieving horizontal scalability, but also allowed us to leverage it for database version upgrades, migrating tenants from single tenancy to multi-tenancy and vice versa, and also for tiering. And finally, as an infrastructure engineer, manager, or an executive, whenever you're faced with this unmet product engineering need, you can use these guiding principles to make decisions around building a technology in-house versus buying it. So build a technology in-house if it makes sense and when the technology drives key long-term strategic advantage, requires reliability, scalability, performance, security, compliance controls, or look at the 3 to 5 year ROI and de-risk vendor lock-in and vendor's region footprint. On the other hand, prefer buying solutions when you are looking to get undifferentiated capabilities and focus your resources to leverage opportunities and provided the third-party provider meets your security standards, offers a viable cost structure, and aligns with your regional and cloud strategy. We also bias towards build for capabilities that drive long-term strategic and competitive advantage. And yeah, we spoke about cost, vendor lock-in, vendors, region footprint, so on and so forth. Yeah, so I think that's mostly it from us. Thank you so much, folks, for taking the time to listen to us and being here today. Thank you. Yeah.